Welcome to this presentation about requirement validation. So today we're going to talk a little bit about this new functionality. So it came out in 14.3 and the kind of things that we are doing with it. Mostly we have been exploring all sorts of application examples, and I'm going to show a little bit of the language that we have built around it, the things that you can do with it. Just play a little bit with it and the kind of models that we have worked on with this kind of functionality. Right, so just to go back a little bit, in case you're not familiar with it, so System Modeler is a tool where you can do all sorts of multi-domain modeling. So you can easily connect components for all sorts of fields like thermal modeling, electrical modeling, mechanical modeling. You can create all sorts of complicated or more elaborate models from these basic components. So you can get all the way to a full robot, for instance, in this particular case. And when you kind of model all of the systems, a lot of questions that arise are whether this system is actually accurate or whether it is actually matching the kind of conditions that you have for your system in real life. And these kind of conditions can take all sorts of ways. So basically we could have something, your requirements could be basically physical requirements just to check that your model is behaving accurately, but they could be just as well like safety requirements or design constraints or performance requirements. And all of these are phrased in very different ways. Sometimes they're as simple as this quantity shouldn't be above this amount, or this quantity should be below this amount. But sometimes they are a little bit more complicated. For instance, you can say something like, in this particular case, we have in flight, when one engine is off, their distribution circuit must provide nominal performance. Or sometimes it can be a little bit more complicated. Whenever the heating is turned on, within 300 seconds, the room temperature must be between 19 degrees and 21 degrees. And of course, you can immediately see that if you start raising the complexity of those statements, you start requirement and more elaborate language. For simple requirements, you can always do very simple things. So for instance, something that we have been already supporting for several years is the function system model uncertainty plot, where you can just specify your system and specify sources of uncertainty in your system, like parameter values or initial values, or maybe disturbances in the inputs. And then we just sample these sources of uncertainty, we simulate the model, and then we plot the uncertainty over the outputs that you are interested in. So for instance, in this particular case, if you have a model of a camera for camera stabilization, and then you have a requirement like a stabilized camera that is disturbed by a force must not move more than 2 centimeters. Then you can easily verify this requirement by just making this kind of plot with uncertainty plot. And in this case, what we are doing is just providing a source of uncertainty in the input for the force. So you have this disturbance. We perform all the simulations, we aggregate the data and the results, and we produce this kind of plots where you can visualize easily how badly your system is doing and how much, what kind of distribution your system has with respect to those sources of uncertainty. So this kind of graphical validation is pretty straightforward. You can do this. You have been able to do this. You can also do things like plotting conditions in system model plot. So you can plot basic logical statements. So you have a model and you have an expression that is a Boolean statement of your variables in your model, then we can plot that easily. So for instance, here we're plotting when y is, okay, so we're plotting the Boolean statement, y is less or equal than 1.5. And then you can easily see that this is true here, this is false here, and this is true here. So this kind of easy Boolean statements that are time fixed. This you can easily verify graphically for your system. The kind of statement that we're verifying here is, for instance, at no time the control signal should exceed 1.5. And then you can easily make this plot and visualize this requirement. But we want to go, usually you want to go further than that. You want to do all sorts of requirement validation processes. Maybe your workflow requires you to provide more information about where it failed. You probably want to display these results, or maybe you want to quantify these results, or maybe you want to make more computations and analysis with the results of your validation. And all of this is allowed by this function that we created, which is SystemModelValidate, where we just accept your model, your requirement, and we perform the validation that you access to perform. So for instance, in this particular case, when we go to this previous example of the model, we have at no time, again, the requirement at no time the control signal should exceed 1.5. Then we just pass, again, the model and the requirement to SystemModelValidate. And we produce, we verify if this statement is true or not. So in order to do this, we are using here as some new functions. Something, in this case, we're starting with system model always. It's just one way of expressing that a statement should always be true. And we're just saying, we're just stating here that y should always be less or equal than 1.5. So this is our language for the requirement. We're just passing that to SystemModelValidate, and SystemModelValidate is performing automatically the validation. So I'll speak a little bit more about the language later. And the kind of things that we can do with uncertainty. But for now, we can just see the kind of information that you can extract from this object that you get from the validation. You can extract things like a failure plot, which is going to decompose your statement into more basic statements and then make plots when they are true or false. In this case, the statement is very simple. So we are just plotting when y is less or equal than 1.5. You can extract also the failure intervals, so where these things failed. And the fact that you can extract these failure intervals means that you can do all sorts of computations with that. You can pass this directly to arc length and then compute for how long this statement wasn't, this requirement failed. Or you can just directly produce the interval plots. But this is the kind of things that you can extract when you perform things, when you perform a single validation. But obviously, when you validate things, you want to take into account uncertainty in your system. And that's when other properties are going to be more interesting. So for instance, in this case, we go back to the model of camera stabilization, and then we say, again, we want to check that the camera doesn't move too much because we are stabilizing it. So we are passing the same source of uncertainty to the camera. So we are acting with this disturbance to the camera, and we are just checking this statement. In this particular case, our statement is, again, just a statement with system model always. We're just saying that we want the position of the camera to not oscillate further than 2 centimeters away. So this is a very straightforward way of stating that requirement. And we just pass the information about the uncertainty and the amount of simulations that we want to perform. And this particular case, where we have uncertainty, what we're going to do is we're going to perform several simulations, and we're going to specify a success rate that is not just 0 or 100, but it's going to tell us how many failures we had and how many simulations we performed. And of course, we can extract things like, now we can extract things like the success probability of our validation. We can extract information about the configuration that caused the system to fail. So for instance, you can decide how many failure configurations you want to store. By default, we only store one, but there is an option where you can say how many configuration failures you want to store. And then by just extracting this property, you can extract the actual force that caused our camera to oscillate more than 2 centimeters. And we express that in such a way that you can just pass directly that output to SystemModelPlot and replot the system, and indeed visualize where the camera went down, in this case, for more than 2 centimeters. Yeah, so this is one way of extracting information. This is one way of presenting your results. And you can always also as well also extract all the XSS configurations if you're interested in that. So in this case, all these forces didn't cause the camera to oscillate more than 2 centimeters. So now we can actually talk about the language. So we're going to go a little bit further than just system always, because not all of the requirements are going to be just as simple as this. So what do we do with this language? So the kind of things that we're going to load here for requirements are, we are trying to cover a lot of space here. You can do all sorts of statements with Boolean variables. So obviously you can do any kind of ands, ors, nots. You can do less or equals, obviously, between real signals or compositions of real signals. And then we have functions such as system model eventually, which is going to tell you, is going to one way of specifying that you want this requirement to be satisfied at least once in a specific interval. So it's kind of like the moral opposite of always. Always needed to satisfy it always. Eventually, it should satisfy should be satisfied at least once. System model sustain. So system model sustain is when you need something to be true for a specific duration of time. Maybe you want it to last. This has to be true for more than 2 seconds and less than 5 seconds, for instance. Or maybe it's something like you want something to be true for at least 2 seconds, or maybe you want something that is true for at most 5 seconds. So this function allows all those kind of specifications. We're going to see examples for these functions right away. System until is when you want to say that something has to happen, has to be true until something else has to be true. So this depends on actually 2 expressions. And system model delay is when things actually, when things can actually have some kind of inertia, and then things can, maybe your system is not like completely precise, or maybe you expect some delays between 2 signals. So this is when delay is going to be useful. It just delays the statement of your requirement. So we're going to see a little bit of how we use these 3 functions, but this is the scope of this. So with these functions, you can already express all sorts of complicated statements. So for instance, you can say, in this model of the circuit, you say the DC voltage in the rectifier should not exceed 540 volts for more than this amount of time. So one way of expressing this is by using system model sustain. So what we're going to say is, we're going to check when the voltage is actually greater than that amount. And we're going to check that it isn't true for more than this amount of time. So we're going to say, we're going to check for the cases in which it's true for longer than 0.02 seconds. And then we demand that this should never be true. So we just put a not before the statement. So this is a not. So this is our way of saying this should never happen. So this is our requirement. We pass it to our model of a circuit. We validate. In this case, it fails the requirement, and then we visualize what it failed. So here we see how it's decomposed. So basically, we find that it fails in this interval, and indeed, when we compute the length of that failure interval, we find that it was true for more than 0.202 seconds. It was a little bit more. So indeed, the requirement failed. So this is one way of using system model sustain. If you're interested in system model delay, so we have this example of a model of system of tanks, interconnected tanks. And so our requirement is whenever the water level in the first tank is about 1.2 meters, and for at least 6 seconds more, the water level in the second tank should be above 0.6 meters. So as you see, this condition that it's not, we don't only care about when this is true, but also for any 6 seconds more than that time, those time intervals, these other conditions should be satisfied. So in a whole, this is like an implies. This should imply this. So the requirement that we have here is again an implies. So this implies this. So our second condition is that the height in the tank should be greater than 0.6 meters. And our first condition is specified like this. So when the height in the tank is greater than 1.2, and 6 seconds later than that, so and even for 6 seconds more, this second condition should be satisfied. So this is how system model delay we're using it. And there are other variations of system model delay. This is one way of using it. And here we see that we validate that it fails, and we see how we decompose the expression. So here we have the places where the height of the tank, second tank, is greater than 0.6 meters. Here we see when the height of the first tank is greater than 1.2 meters. Here we see the effect of the delay. So the delay is just adding 6 seconds more to when this interval was true. So this is why this is wider. And the statement, our requirement is that whenever this is true, this should be true. And what we see is that there is a small interval here, a small gap here, where this is true, but this isn't. And you can see that in the plot that the water level in the second tank goes below 0.6 meters too early. We plot the results of the simulation. So this goes down too fast, this becomes false, and then necessarily this becomes false. So this is a way of exploring our requirements. And finally, for until, we have something like this. We have a control system of an inverted pendulum. And our statement is whenever the angular velocity in the motor is below this angular velocity, until the position of the car reaches this distance, the angle of the pendulum must be between this and this. So again, this is an implied statement, but the first statement is an until. So here is where we have this until at the start, and here we have the composition. I may have to jump a little bit in the details, but this is the fundamental picture. This is the full spectrum of statements that we're using. And one of the nice things of this functionality is that not only it allows you to find where a requirement fails, it allows you to pinpoint where it fails, and also you can immediately start fixing your model or trying to find how to make it work or satisfy your requirements. So for instance, in this particular case, I have a bigger application example. This is an electrical vehicle. And we demand that the temperature in the battery should only be above this temperature for at most 8.5 minutes. So the way we write the assignment is the temperature should be only greater than 28 degrees Celsius for at most 8.5 minutes. So we use the same trick. We use system sustain, and we use the NOT that I explained previously. And indeed, we see that for this particular configuration of our electrical vehicle, it fails. There is this long interval where this fails. You can see the plots that it actually fails in other places, but the failure intervals are not longer than 8.5 minutes. Here it actually goes for longer. It goes hotter than 28 for longer than 8.5 minutes. So this is where it's failing. But we can immediately say, okay, well, if this temperature is going too big, then maybe what we should do is just consider a configuration of our electrical vehicle where the resistance is lower. So if the resistance is lower, the temperature, physically speaking, the temperature should go, we would expect the temperature to go lower. And indeed, if we just reduce the resistance in our in the battery of our electrical vehicle, then we simulate with passing the same requirement that we wrote previously, and then it validates. And then we can make the plot, and we see that indeed it's still actually, the battery is still going up above 28 degrees in some intervals. But if we compute the interval lengths, we actually find that they are less than 8 minutes compared to the other configuration in which the intervals could actually go above 8 minutes. So this is kind of the power of the functionality. You have because this is now extracting useful information for you, and this is all available in the Wolfram language, then you can pass it to other functionality, use all the power of the Wolfram language to improve your model, make it better. We have been exploring this in all sorts of fields, and we have made community posts about this. So we have these blog posts using this validation functionality in aeronautics. So this is about validating high aerobatics with SystemModeler. We have explored this with electrical vehicles. We have explored an example on thermal runaway in chemical manufacturing and how we can use this validation functionality there. And we have also used this in a model of a model that uses an algorithm to avoid aircraft collisions. And then we apply the validation functionality there as well, just to see if how this model fares against our configurations. So all of these are very interesting. I recommend them. They are already linked. They're linked here in the notebook, so you can just check them. And I guess that's basically what I wanted to talk about. Just show a little bit of like the things that you could do with this functionality, the kind of workflows that you can explore, and making the case that basically we are trying to provide like full comprehensive support for this kind of requirement validation workflows, and just also to make them as easy to use as possible. Yeah, so I guess that's what I wanted to say today. So let me go back to questions. Right. Yes. Okay. So this says, can you show in SystemModeler the inside of the model just to SystemModelValidate? Oh, right. Sure. Okay. Yes. I guess we could go for any of the models that we have here. Perhaps the camera stabilizer, I guess. So one quick way, if you have already the system model displayed, quick way of getting it into SystemModeler is just to do a right click, and then you can do open in SystemModeler Model Center, and then you see the model there. Yeah, you can access all the components, etc. So you can do this with any of the models that we have in the notebook as well. We can do this with the simple electrical vehicle as well. There it is. Yeah, so that's one quick way of exploring the models. Are the conditions of SystemModelValidate equivalent to the Modelica logical or math Boolean toolboxes elements we can use when building the model? Yes. Basically, well, so the things that you have in MSL in the Modelica standard library at the moment, they are usually the kind of thing that you have here. So all of these things can be expressed in the Wolfram functionality as well. Things like Thor, NAND, for all of this we have a Wolfram language equivalent. Rising edge, falling edge, changing edge, and on delay. I think we have, it's possible to express this also with the language of SystemModelDelay, if you're interested. So you can actually pinpoint these times as well if these are of interest. And then there have been other attempts in the Modelica world of like validation libraries with more complicated Boolean statements. But usually, I think it's possible. In general, it's possible to find equivalences of these statements with the functions that we have available with SystemModelValidate. Is it possible to see the list of parameters a user can choose in SystemModelValidate? Parameters as in the model parameters, or so if you are referring to the model parameters, then just put those model parameters are available in the model. If you want to see like all the possible arguments that you can pass to SystemModelValidate, one way of doing it is by going to the documentation as usual, and then you can see that Okay, things that I probably didn't mention. Okay, so you did indicate that you can specify how much failure configuration, how many failure configurations you want to store, how many simulations you want to perform, all the properties that you want to extract, and how you can express the uncertainty around your parameters and your inputs and your initial values. So I would just recommend going to the documentation. I think it's we have tried to cover all the possible scenarios. So that's, I think that's what I would recommend. The first model about, okay, so the first model, right, the first model that we, okay, so all of these are the MSL models. Again, as I indicated, these can all be found by just doing left right click, and then you can go to the full robot as well. That always looks nice. So yeah, just right click and show in the model center. That's what I would recommend. And yeah, I guess if there are no, we can wait a little bit for more questions, but for now, this is probably what I wanted to share. Just do this in case something else shows up. So yeah, as I mentioned, just to finish, I would recommend going to the posts. So we put a lot of work into writing this. And these also have nice animations and visualizations. So this is always fun. It's always fun to work with the aircraft library because you can see everything in play. Yeah. Right, and then here we, for instance, explored when things are risky for the planes and the passengers, well, and the pilots, very much motivated by the work that Eric has done in aerobatics. So I strongly recommend his presentation from yesterday. Very nice as well. Okay, so I guess if that's all, then we probably can leave it as that there, and we can stop there. So thank you so much. Any questions, just reach out to us.